What up, everyone? This is LeetCode 191, number of 1 bits. Write a function that takes the binary representation of a positive integer and returns the number of set bits. It has a set bit refers to a bit in the binary representation of a number that has a value of 1. So, yeah. Basically, you're just given an integer and you need to consider how many ones does it have in its binary representation, and you have to basically count up the number of ones. Right? This is the binary representation of 11. It has 3 1 bits, so you have to return 3. Likewise, for 128, it has 1. This is the binary representation. It has 1 bit, so you return 1. This is the binary representation of this number, and this has 31 bits, okay? Now, there's really a couple ways to approach this problem. I'm just gonna go with the straightforward approach first, which is basically, um, we're just gonna AND the integer with 1 in bit shift. Okay, so I guess I'll explain it before I write any code, just so you're not confused. So basically, we're just doing this is the binary representation of 11, right? So we're just gonna AND this bit representation with 1, right? Okay. And if the result is 1, that means that this bit was a 1, right? Because when you AND 1 and 1, you get 1. So when we AND the last bit by 1, if we get 1, we increase our counter, okay? And we bit shift. So here, right? 1 and 1. So because our result is 1, we know that this bit is a 1, okay? So we would have a counter, right, to count the number of 1. So we would increase this. We'd go from 0 to 1. Then we would left shift this, okay, by 1. Do it again, right? And this bit by 1. Well, we also get a 1 as a result, so our count goes up by 2. We're gonna left shift this. Okay, now here's where we get 0, right? This bit is not a 1, so when we do 0 and 1, we get 0, okay? So we're not going to do anything to our counter. We're going to keep left shifting, okay? Okay, 1 and 1 gives us 1, so we increase our counter by 1, okay? Left shift and we get 0. Okay, now n is equal to 0, so that's where we would break out of the while loop and return count, which is 3, which makes sense, right? Because we have 3 ones in the binary representation. Okay, so yeah, we're just counting the ones by ANDing the binary number by 1 and bit shifting. So we go through all the bits in the representation of whatever our integer is, okay? So while n is not equal to 0, we're gonna say if n and 1 is equal to 1, then our count is gonna go by 1, okay? And if n and 1 is not equal to 1, then we're not going to do anything to our counter, so don't even have to worry about that. And then here is where we're going to bit shift by 1. We're going to right shift, or bit shift to the right by 1 bit. And we're basically just going to do that in the while loop until, again, we go through all the bits. And when n is equal to 0 is when we would exit, and then at that point we just return count. Okay. Yeah, just know your binary or your bit manipulation, and make sure your binary, basically your understand how to manipulate bits, and kind of make sure you brush up on your binary knowledge, and you should be fine with this simple solution. Now, there's a more efficient solution. That's I mean, it's the same time complexity, but it's a little bit more efficient, where you're not considering every bit, you're only considering the ones. So instead of doing 4 operations, we would do 3. And okay, let's get into that. It can be a little bit confusing to understand. So the way we do, let me just write the code first and then I'll explain it, just so it's a little bit easy to understand by me pointing out the code, okay? So there's another way we can solve this problem, right? And we can do it by basically taking n and anding it with n minus 1, okay? And every time we do that, we increment the count by 1, and we return the count. Okay. I'm going to go through an example here, okay? Just to kind of explain what this is, okay? So let's say our input n was the integer 108. Okay, this is the binary representation of 108. So when we're in the code, okay, while n, so we would enter this n, and we would do what? We would do n and n minus 1. Well, n minus 1 is what? 107? Okay, so what's the binary representation of 107? It's this, okay? So let's AND this, okay? So the result would be 1, 1, 0, 1, 0, 0, 0. So what we're doing, okay, every iteration of this while loop, what we're doing is we're getting rid of each least significant 1 for every iteration, okay? So if we have 3 1s, well, in this case we had 4 1s. So if we have 4 1s, we're doing 4 operations really. So what our loop is doing, it's that it's turning off the least significant 1 in every iteration. So when we subtract 1 from n, what we're doing is we're basically flipping every bit from the least significant 1 all the way to the right, okay? So for example, this is our binary representation of 108. Our least significant 1 is what? This one right here, okay? So we're flipping this bit and everything to the right of that, okay? Now, let's go over the next iteration just so you kind of understand. By the way, every time we do this, we increase our count by 1, okay? So our count right now is 1. So what is this result? This result is the binary representation of 14, okay? That's what it is. That's what this result is. Our resulting bit. Okay, now n minus 1. Okay, so n minus 1 here would be what? 14 minus 1, so it'd be 13. What is the binary representation of 13? Sorry, not 14. I'm dumb. Sorry. Don't mean to confuse you. 104 is what I meant to say. 104. So what is the binary representation of 104? It's this result, okay? So n minus 1 is what? 103. What's the binary representation of 103? It would be this, okay? Now, pay attention. This is our least significant 1 now, right? Right, because we have this. So our least significant 1 right now is this. See how we flip this 1 and everything to the right of that, right? Because we have 1, 0, 0, 0, but that changes to 0, 1, 1, 1. Now everything to the left here is the same, right? Likewise here, this is our least significant 1. Everything to the left is the same. It's every iteration, the least significant 1 and every bit to the right of that, those all get flipped, okay? Notice this is our least significant 1. So the result here should be 0, 1, 1, 0, 1, 1. Okay, this is this should flip to 0, 1, 1, 1, 0, 1, 1, 1. See what I mean? Every least significant 1 and all the bits to the right of that get flipped every iteration, okay? So let's AND this, okay? This is the result would be what? 1, 1, 0, and this would be 0, 0, 0, 0. Okay? Yeah. Okay. What is this? Oh, yeah. And our count goes up by 1. What is this the binary representation of? This is the binary representation of 96. Okay? And I did this beforehand just so you don't... I mean, you can double check the... If you really want to count up the... Convert the binary to a decimal, you can, but I did this already beforehand just to make it simpler. But you can double check my work if you want. Okay, so n minus 1 would be what? Well, n right now is 96, so n minus 1 is 95. The binary representation of 95 is this, okay? Pay attention. Least significant 1 right here, right? So theoretically, like I said, this 1 here is the least significant one. This should get flipped, and everything to the right should get flipped. Well, what do you know? This 1 got flipped to a 0, and all these zeros got flipped to a 1. Okay, let's do our result again. ANDing. Okay, 1, 0, 0, 0, 0, 0, 0. Okay, again, our count goes up by 1. So this goes up to 3 now. Okay, now this number here, what is this a binary representation of? This is the binary representation of 64, okay? That's what it is, okay? Now, n minus 1 is what? 63, right? Okay, what is the binary representation of 63? Okay, it would be this. This is our least significant one, right? So this gets flipped and everything to the right gets flipped, okay? Well, what do you know? That's what happened, right? When we AND n with n minus 1, okay? Let's do the result again. When we AND these two together, what do we get? We get 0, 0, 0, 0, 0, 0, 0, okay? And, again, every iteration, our count goes up by 1. Well, now we would exit the while loop, right? Why? Because, honestly, instead of saying n, because in case I confuse you, I'm just going to say while n is greater than 0. Well, we would exit the while loop. Why? Because n is equal to 0 at this point, right? Or rather, n is not greater than 0, right? N is not greater than 0 at this point because n is 0, okay? So at this point, we would exit the while loop, okay? And we would return count. What is our count? It's 4, right? Does that make sense? Yes. Why? Because we have 4 bits that are 1, right? Okay? So I hope you can see how this second solution works. I know this video is a little bit long. I apologize, but I just want to go through this example step by step just so you kind of understand. But you see how we only really did 4 iterations, right? Why? And there are 4 1 bits, right? 1, 1, 2, 3, 4. We only did 4 iterations, right? So this solution in this code is slightly more efficient than the first solution I showed because you're not going through all these bits, right? You're not going through all these bits. You're only doing 4 iterations, right? Basically, you're flipping this 1 and adding to the count. And then you're flipping this one and adding to the count. And you're flipping this one and then adding to the count. And then you're flipping this one and adding to the count. And you keep doing that until you get basically a result binary representation that's 0. At that point, you exit the while loop and you return the count, and that should give you the number of ones that you had, right? But yeah, I thought I would show you that visually, right? How you're flipping the least significant one and all the other bits to the right. Every iteration. I thought I would show you that just because it's a little bit more helpful that way. Yeah, there's quite a few videos on this problem, but I feel like a lot of them don't do that good of a job visually. Some of them do, but not all of them. But I just wanted to do with a really big number just to kind of show you what we're doing and how this algorithm's working, but visually how it's working. So yeah, let me delete that. Run this. Submit. So yeah, this second solution is only slightly more efficient. Maybe in an interview they would want you to have this slightly more efficient solution if they're like really picky, but yeah. But honestly, it's not that hard to come up with this second solution so long as you understand what we're doing here, right? If you understand visually and kind of logically what we're doing by flipping the least significant one, it's not hard to come up with this in the future. Even if you don't remember the code, it's not gonna, as long as you remember this process, it's not gonna be that hard to come up with this code, right? From scratch. Even if you don't know what the code is, as long as you remember this process, you know what you have to do to produce the correct code. So that's why I kind of wanted to go through it step by step, make sure you understood what's happening. So yeah, I hope this is helpful. And yeah, I'll see you in the next one.